spoiling myself.
Hey, how's everyone doing? Squidward kind of freaking out right there with the project. Don't let the project freak you out. We've got a stream that we did last week that I think was really helpful. We went through everything on the project so we could, if you're watching this now, which some people probably are, well, hello, say hey in the chat. Check out the stream last week, which was, I think, we walked through everything step by step. Got 435 views on it right now. One of that previous stream right here. You start by showing that. But if you're here in the chat, you got questions, let us know. What questions do you have? There's a lot of homework assignments coming up. Send them over. What question? I had a question on the project. Could you explain the 0.5, the highest hypothesized value? Yeah. So, yeah, that's a really good question right there. Let's talk about hypothesized and hypothesis tests. It's for the one sample Z. Yeah, let me go to the video right here. Add that in. May 1st office hours. So, the pin. Let's put this as Tom Stamp right here. Okay. 2, 3. Stat 201 project. One sample Z hypothesis test. Let's go over and check that out. Okay, so I want to pin parts of this video right here. We've got the one sample Z hypothesis test, and we're going to talk more about hypothesis test right now. But I want to point out that when you do hypothesis test, we have a method we call the HACS method right here. There's Brian, current, past, present, future, using the, now you won't write it out as the notation, you'll write it out in words. So it's important to understand what hypothesis tests are, how they work. And I'll put the link to this video, which has every step of the project. We'll pin this time. So project video. And then let's talk about this a little bit here and explain what's going on with this. We'll pin that message. So when we do hypothesis tests, what are we doing? So the first step, you're welcome, Janelle. Good questions right there. Let's throw you some points right here. Is Mubot? I don't even think Mubot's, oh, well, maybe he never went to sleep. Maybe. Let's wake him back up. Here we go. Wake up Mubot. There we go. So what is our method we use to solve problems like this called, Janelle? What is the method we use to solve problems like this? So the video is more kind of direct on the project, but I also want to explain the steps and the process and understanding how to do this. The HACS method. Great job, Janelle, right there. Well, Mubot will wake up. We'll throw some more points here in a moment. So you might be wondering, if you're watching this, what is the HACS method? And once again, read over the rubric, look at what the rubric asks you, directly answer everything on the rubric. The grader's going to click the buttons to give you points. So whenever you're thinking about what do I need to say, look at the rubric, but you also want to understand what you're doing. It's not about just like filling out a form. It's like, why am I doing this? What does it mean? Here's the HACS method right here, standing for, we do a hypothesis test. Nice job, Janelle. Great work. Hypothesis, annotate, notation. We have here check conditions. And then we solve for p-value. So these are all the steps right here that we do, and you can look at it with some jump output and kind of see the same sort of methods. So we're going to go over to the Diamond data set. So this is our Diamond data set, a data set that you will not be using for the project. It's not one of the 4 data sets that can be used for the project. You will be using this data set right, or a different data set, not this data set. And you will have your random subset of the data. So with this right here, hey, Maisie, good to see you here. Anytime you're doing a hypothesis test, you need to first create the output for it. So when you do a one proportion test, which is the one proportion Z, you're using what kind of data? Proportions means your data is what? Proportions means your data is what? Like, this is important to know about the one proportion Z, which we can write out the notation for. Do I still have that Word document open over here? So there it is. Categorical. Janelle's on fire right there. Categorical. So when you do this, you're hypothesizing what the true proportion is. Does that make sense? Like, you are going to hypothesize. So we are going to, we'll decrease one a little bit here. we are going to make a hypothesis, guess, or belief of what the true proportion is. That's what we're doing right now. We're making just an idea. We're just saying, I think this is true. Like, if I told you what percent of UT likes pepperoni pizza, what percent do you think? Which percent is proportion, basically? Percent more as a like a whole number, like 84%, but decimal would be proportion, like 0.84. So what percent of UT you think likes pepperoni pizza? And it doesn't mean it's true. 60%. So in notation, hey, Mora, great to see you here. Got some SI leaders in the chat. In notation, what did you just give me? If you think 60% of UT likes pepperoni pizza, you just gave me what? Like, what did you give me in notation? You didn't go out and take a sample, and you don't know the truth. Those are hints for what you gave me. What did you? Well, kind of, very close, but you're missing something. So that currently says, my null hypothesis is equals 60. That's how that reads. That says my null hypothesis is equals 60. And I think you're on the right track to know right there, because we're missing something. So we need to think about, what are we saying? So that says my null hypothesis is equals 60. That's how that reads. We always try to read it as a sentence. My null hypothesis is equals 60. So what are we missing? So we're trying to we're doing the steps to make sure we understand like what we're saying and what we're doing. So a few questions. We're missing something here. And then what does 60 mean? For the project, you're writing it in sentences, correct? You're explaining it to the reader. So I'm writing it in notation, but then I'm also explaining what it is. So that way I'm not like directly writing it out. And then you want to think about how like what you're saying and what it means. So what is, in notation, what is the green thing? That's what you came up with, right? So in notation, what is this green thing right here? Like the notation for it. Is it mu? Is it y bar? Well, it's a percent, but like, what is it? Is it, yeah, chapter 17 homework? Yeah, tell me which one. We'll do it right here. We'll do that next. Just put it in the chat. We'll do it. Is it N? Is it S? Well, it's not a p-value. A p-value will be from a result. Remember, we're going to solve for a p-value, and this is why I cover these things right here. We're going to solve for a p-value at the end, and p-values are probabilities, but that's not. So remember, this is the value that you hypothesized is the true proportion of people that like pepperoni. So it's the hypothesized proportion. You came up with it, right? You came up with, I think, 60% of people like pepperoni pizza. So what would that be? Don't worry, we're throwing 100 points. Don't worry about getting it wrong. Just take guesses at it. It's what you hypothesized is true. You just came up with it. So what would that be in notation? So you were just like, I think about 60% of people like pepperoni pizza. So what would that be? You hypothesized that was true for the population. So here's what it is in notation as words. You hypothesized that is the true proportion. So what is the notation on 0.60? What is it in notation? 0.60 is the what? Not percent. Well, think, you know how we have like N is sample size, S is sample standard deviation, sigma is population standard deviation, mu is population mean, y bar. Hey, Jesse, good to see you here. Y bar is sample mean. So it's a proportion. What kind of proportion? Well, so p hat comes from where? And this is why I'm reviewing all this, because p hat is from a where. P hat means what? This is really good review. I'm throwing you 1,000 points because I want people to cover this and understand p hat means what. Like, write down each one of these and then think of examples with each one. P hat comes from where? Like, what does p hat mean? It is a proportion, but it comes from a what? Because it's, yeah, no, write all these down and then use examples. This is why we're covering this, because this is what's big for the test. P hat is from a sample because it's the amount of successes out of the sample. So you just came up with this, right? Did you go out and sample UT, or did you just come up with that and say, I think that's true? So that's not the sample portion. Keep up the good work here. This is the practice. You just made this up, right? You just said, maybe 60% is the truth. So let me ask this, yes or no. Is this the truth for the proportion of people who like pepperoni? Is that the true proportion? Is that the truth? You just came up with it, right? You're like, 60%. That's what I guess. It's not the truth. So it's not going to be p hat because it didn't come from a sample, and it's not going to be p. P is the true proportion. This is going to be, does anyone know we'll throw out another 1,000 points. We're going crazy on the points. It is p naught. It is p naught. And the good way to know this is the value over here is always the one that goes with the null hypothesis, and it's the hypothesized. And what you're doing is you're hypothesizing that it is the truth. So you're saying, I am hypothesizing that the truth is equal to what I believe. Does that make sense? So you are saying, I hypothesize that the true proportion of people who like pepperoni is 60%. That's what I currently believe. Does that make more sense, Janelle, right there? That you're saying P right here is the true proportion of people who like pepperoni. And this is my null hypothesis, is that I currently believe the true proportion of people who like pepperoni is equal to my belief of 60%. And the belief is what you claim to be true for the truth. So that's P naught. Like this value in green right here is P naught. Like that is, like, just to make it clear, that is P naught. So if we had done something different and I asked you, so Jesse, what do you, or Janelle right there, what do you think students will score on average on test 3? And what do you think students will score on average on test 3? On test 3, what do you think they'll score? Like, what do you hypothesize? $78? That's a pretty good guess. Yeah, that's not bad either. So 78 goes right here. Now, you're hypothesizing that that's the true average. So what do you think that is in notation? So you can type mu for mu, but 78 in notation, it's not the truth. It's what you're hypothesizing is true. So think about what we just wrote a moment ago. 78, you just said, well, I guess that's true. It might be true. I don't know. We'll find out. We should do some testing to see if 78 is true. It's mu naught right there. Great job, Jesse, right there. It's mu naught. So this right here, the hypothesized value is what goes with the null hypothesis. And we're saying, I hypothesize that the true mean, right there, mu, will be equal to 78. That's my hypothesis for the test. And when we go out and talk to students, for the sample Z, how many sentences should it be? Depends. Just make sure to answer each part, because I'm too afraid to say like an exact amount of sentences. Because if I do, someone might write like 3 sentences, but then they might be really short. So that's where I get worried to say how many sentences. Always look to the rubric, and if you disagree with the rubric, I do get points back. Like if you get graded and you say, I think I answered these properly, I have given people points back. Yeah, I've just had people in the past have said like, yeah, 3 to 5 sentences is good. And someone's right, like I wrote 5 sentences, and the sentence is like, the mean is this, the standard deviation is this. I'm like, but it says don't write the mean is this. You want to explain what the mean is. So with this right here, and the one sample T or Z, and did you put the question, Moira? Moira, drop the question if you want. We'll do it next because we're about to reach a break here. With the diamond data set, and we can go here, we can go analyze distribution. You know what? I think that ideal is only about 25% of diamond sales. So let's go right here and do analyze distribution of the cut of the diamond. And here's the distribution. So man lives in New Sea. Yeah, I'll do the 2 routes. You got it. So here we are with the, well, just noticing ideal right here. I think it's about 25% of the sales. I think I can test only one. We'll find out if I can. So with this right here, we have ideal is 40%. Does everyone understand what this means right here? If you look at this, 82 of the diamonds out of the 201. I do have more than 2 groups today. I think it'll still work. But 82 out of the 201 diamonds, 80 divided by 20 is basically 40%. 82 divided by 201 is 41% or so. And with that, that is the proportion right there of ideal cuts. It's the most common group, but I'm going to hypothesize that it's about 25%. Now, is there evidence against that hypothesis? We have to go over here and go to, or evidence for an alternative, I should say, go to test probabilities. So you have to go to test probabilities, and I would include this as a screenshot. So if you make output and you explain it, you should include it. So we're going to go over here to test probabilities. I think it'll let me just enter in 0.25 for ideal. We'll see what happens when I run this as only one value entered in. And I think it just went and found the other values right there and kind of did an evenish distribution. So you will put in, if you put in 0.5 for one, you only have 2 groups for yours. It will put in 0.5 for the other. And then we get here to the probabilities. So with this, we hypothesize that this is true. And I think it just kind of split according to, it's interesting how it did that. We do this. So I'll show you in the video right here. Where? There we go. Video. For evidence, definitely follow along with this video where here it is right here, where I do it with a, yeah. Well, so definitely 0.5 right here. I'll show you. I'll go back to where I do it. Test probability. Okay. The steps are, talk about a lot. So to do this test right here, we go back. So you want to go back. I'm going to remove the confidence interval just so we don't have as much output. You click under the second arrow right there. You go to test probabilities. So test probabilities, this is going to let you do the hypothesis test. Remember, this video is linked up top. If you want to go and watch it, it has each step. When you go to test probabilities, you can enter in the hypothesized values. This is where you're entering in P naught right here. That is P hat. This is P naught. And also note, I do have the formulas in the background that solve each one of these if you were to do them by hand. We do test probabilities right there, and we enter in 0.5, and you get the test, and we'll use the Pearson test with the p-value. So you're actually doing the HACS method right here, and I want to point out that I put the formulas here for a point because I want to make sure we understand like what we're doing, and you can see right here, we are doing the purple formula right here, 0.5 for both. I think if you enter in for one, it'll do it for the other because it has to equal up to 100% because that's the laws of probability right there. But notice how we have p hat, p naught. P hat is the value, and I think I mark all the notation. Well, I did right there. I should have marked it also for the hypothesis test, but I go through what all the notation means and also what you're doing with the test, which is very important. We don't want to just think about it as, oh, we just got output. We want to know this is p hat, that is p naught, and then the p value down here is the end of the test. So once again, remember, we are doing this to do the HACS method, and we can find the p value right here at the end, which JMP is going to supply for us. So JMP does give me the p-value down here at the end. The p-value is going to be under the Pearson, and the p-value is evidence to me that 0.25 is not the truth. Now, when you look at this, if we go to confidence intervals, don't make a 95. It says don't do that for the project. When you make a 95% confidence interval, what do you notice about the interval for ideal? The interval for ideal, what 25%? So do you see 25%? Or look at the interval for ideal. And what about 25% is interesting here? So if we put this right here, you see the 25%. What about my interval? Look at the interval right there. What about 25% is interesting? Or what would you tell me? We're speaking specifically about the lower and the upper right here of the interval. The lower and the upper, what is interesting about this? Well, we could interpret it. Well, we could say I am 95% confident the true proportion of ideal diamonds that are sold by this store is contained in the interval 34.2 to 47.7%. But what about 25% do you notice about this interval? What about 25% do you notice about this interval on the right? 25% is what I hypothesized, and then look at the interval. So 25% was the hypothesized truth. So what do you notice about this interval? Number 9, what's the interval? Is it the quiz or is it the homework, Moira? It's not in the interval. So if it's not in the interval, we can what it. So if it's not in the interval, look down here, which the test also confirms, we can what it. The homework, perfect. We can reject it. Janelle, perfect answers right there. So 25% is a value we could reject, and thus we also see it's not inside the interval. It's just not a believable value. And the Pearson test confirms this also. So when you look at the p-values down here, it's important to notice that if you're testing probabilities and those probabilities are not within your interval, those are values you would reject. And that's what the project's pointing to. So this is the whole project. What do we write in sentences? Well, we need to explain that. But once again, remember, I'm not going to say exactly what to write because I can't tell you exactly what to write. But we'll go look at the project real quick over here. And remember, the project's going to walk you through these things and say, like, you know, what do you notice about this? What do you notice about that? Here, we'll go look at the rubric. 100%. Remember, the graders are going by the rubric. So when we go over here, since Well, then you want to explain what you want to explain in pretend you're talking to your parents about this, and would your parents understand what you're talking about? Like, reject means no longer believe. Like, I don't think that that's true. So it says right here, hypothesized value. Hypothesized value clearly explain why is important to the company. So these are things I haven't done while I've been talking about the project. So once again, remember, the graders are clicking the rubric. I want to make everyone very clear on that. So hypothesized value clearly explain why it's important to the company, why you think that 50% is true, and why that's important to the company. The hypothesis of a two-sided does not equals hypothesis test clearly so explained without using statistical notation. So that's where we talked about what does it mean to hypothesize something is true and believe it. And then the two-sided is the does not equal. So either it's equal to that amount or it's not equal to. Explain the conclusions your company makes about the test and how they arrived at their decision by using the confidence interval. So you also want to explain using the confidence interval, like, which we just, does that make sense? Like, I think this should be very, very clear with what we did right here. Great interpretation that follows the notes. So you want to probably interpret your confidence interval, talk about why you believe that value or don't believe that value. And I'd also show the hypothesized test and then kind of mention the convergence or non-convergence of that test. Does that make sense, Janelle? So I think that should do it right there. So this right here, like, explain the conclusion your company makes about the test and how they arrived at their decision by using the confidence interval. So we were talking about that just a moment ago with the inside outside and the reject not reject. And then like, what does it mean to reject that value? Like, what are you saying? Like, I reject it. I don't think it's true. So your company would have evidence against that. Which parts are you wondering about? And then we're going to do more as question here next. So there's the confidence interval with interpretation. So since we use 0.5, good questions, Janelle. And then when you run the test, the p-value will be what? High or low? The value is not contained within the interval, correct? And your p-value will be high or low when it'll be low because you're going to reject that as a hypothesized value. Exactly. Does that make sense? Close to zero, low. Because if it's low, then it's unlikely what you saw was unlikely given the null is true. Yay, Janelle, 1,000 points. Janelle, just keep the questions coming. This is all about a conversation. That's why sometimes if I talk a whole bunch, it's like sometimes people get lost because then I don't like. It's like if you're walking with your parents and you're a kid and just let go of your hand and walk away. You're like, where am I? What's going on? But you gotta be like, hey, wait, what are you doing? Where am I going? How are we doing this? So make sure to ask questions whenever you got them. And great job, Janelle, right there, earning some big points. Let's do more of this question here. Here we go. Okay, we got question 9 on the homework, chapter 17. Let's get that going right here. Chapter 17, question number 9. Which one is it? I'm wondering. Question number 9. Okay, let's do it. Property. Okay, so we got some waterfront property right here. And the first thing we see is we got a bunch of what? I'm going to go ahead and mark this in the video. And what should you think about marking right now? While I'm marking this in the video, what do you think you should be marking? What do you think you should be marking while we do this? Which it's basically already done for us.
Notation, brother.
All the notation, right? Now, what's interesting is they want you to make a 95% confidence interval to start just like that. So we need to know the notation for a 95% confidence interval. We're going to go ahead and copy paste our thing right here. Now, there are some trickier parts to this, but it gives us a lot of help on this question. I feel like I'm not allowed to answer things. Oh, you are. You're more than allowed to answer things. We're glad to have you here. More 100 points for everyone. You're more than welcome to be here and ask questions and answer questions. That's, you know how it is. You're from our class. You know, we're here for everybody. So the big part about this, which makes this question not fun, is all the decimals. Now, in truth, if we are running analytics like this, this is how we'd actually solve something like this. I just want to show this really quickly because a lot of times it can seem like, gosh, statistics is so much work. It's like really just so cumbersome. But in truth, it really goes something like this, where you have a data set where you have like males and you have like the heights of males. Sure, that dude's really tall. And so you have, I'm just entering random numbers basically. There we go. And they have females. And all you do, the hardest part a lot of times is collecting good data. So you go out, you do this, and then you do t.test, males, females. There you go. 2 sample t confidence interval created, all calculations done for us. I am 95% confident the true difference between means is contained in the interval. There to there. All of it done. Problem is you have to understand what it means and what we're doing. That's why we teach you how to do these things, because what are we trying to do? In a 2 sample t-test, you have what? 2 groups. Does that make sense? You have 2 groups. Males, females. 2 groups right there. Then you are going to compare the 2 groups on a quantitative measure. So if you look at the MyPearson problem, you have 2 groups. 2 groups can be displayed by side-by-side box plots right here. So you got 2 groups, not waterfront property and waterfront property, being compared on the sale price. And it's pretty clear and pretty obvious just by looking at it that waterfront property is selling for more, and I'm comparing medians. This also goes to the project, which has side-by-side box plots. And if we were to compare these, I would think there's evidence of a dependency. So we're kind of even talking about the project here, by the difference in the medians. We got differences in the maxes. Those are the biggest differences, and Q3 differences and Q1 differences. And the minimums are pretty similar. So the big difference is the more up the arrows go or down, the bigger the differences between the distributions and the more evidence of a dependency. So yeah, that is what we got going on. The 2 sample t-test. Remember, T is for quantitative because Mr. T is mean if you're doing drugs. And then the 2 samples means from 2 groups, i.e. sample 1, sample 2. So we're going to go ahead and take the data over here again and start doing the analysis, but we need to know what we're doing, which is what we just explained right there, why we do a 2 sample t-test. And then also, it's usually pretty easy to perform if you collect the data properly and then just run the analytics on it and then know how to interpret the analytics. So with this, let's go over to our WordPad. That was a 2 sample t right there, it looked like. Okay, so the 2 sample t confidence interval equation is, it's going to be y bar 1 minus y bar 2. What is that in notation? And Maura, you can answer anything you want. What is that in notation? So if you look, this stands for sample mean, and then it's just the groups. So we can start putting ones next to this. And I got to make sure I subtract them the right way. So that's just the what. Like, what does this mean right here? Sample mean 1 minus sample mean 2. So that's just the difference, right? Like, what is the difference? Like, first, let's find what the difference is. How much higher or lower is one than the other? And right now, this interval will turn out negative, and I feel like they do want a positive. Do not include dollar signs. Use ascending order. I feel like they do want a positive interval, because the way in which you subtract them is going to make a thing right here. For the regression portion, do we still look to see if it's statistically enough again? Yes. Yep. You can definitely mention if it doesn't pass the 2 conditions, but yep. And then we go plus or minus, and everything after the plus or minus is known as a what? Everything after the plus or minus is known as the what? Everything after the plus or minus is known as the what? This whole quantity after the plus or minus, margin of error, exactly. So that's the margin of error. The margin of error has a t statistic with 2 complicated degrees of freedom, the Welch's degrees of freedom. We don't calculate that by hand. And we put a star because it's related to a % confident that we are. And then last but not least, we have the standard error here, which is S sub 1 squared over N sub 1. I was going to write a 2 for some reason. Probably could square it, plus S sub 2 squared over N sub 2. So this is the standard error right there, the last portion. Standard error is going to be based on the amount we sample and the variation, which is the standard deviation of the data. And so with this, we can put in the numbers right here. I do feel like the interval is going to be positive, so please wait till the end of this question. As The Rock would say,
it doesn't matter.
just going to change interpretation. I hope they would accept both answers. So I am going to do 2 minus 1. If we get it wrong, it's because it's negative. We'll find out the hard way. This doesn't matter if you mix it up because you're adding them together. So the harder part for a lot of people is finding this t statistic, and this is usually where errors occur. I think it said make a 95% confidence interval. So what value for t comes to your mind, or z comes to your mind for 95% confident? When you hear 95% confident, probably a lot of students who've been working really hard at this have a value that comes to mind. I think it might have just appeared in the chat. Oh, they want waterfront. Oh, good, good, good. Oh, Jesse, where does it say that? Does it say that? Jesse, great job. I'll explain how much more waterfront property is worth. Jesse figured it. Jesse, 1,000 points and more at 1,000. Let's just throw 2,000 points. You both are very correct and great practice right there. And Jesse's correct. They want to know how much more. So they do want a positive interval. It is part of the question. They do make that clear. So it is meant to be positive. Waterfront minus non-waterfront for a interval that has positive numbers. So, or for a positive difference and probably positive interval. So we need to go over here to the t, and then we could calculate the degrees of freedom ourselves. But the good news for us is that this question, what? It gives you the degrees of freedom, 108.08. And so we're going to put that right over here, or put that right there, 108.08, and go between, and there's the t. Now, I would carry it to 4 decimals, 1.9822. 1.9822. That is our t. As the t gets more degrees of freedom, it approaches 1.96. So if you start here at the very bottom, your t will approach 1.96 and the curve will become more normal. This is the student t distribution that William Gossett created while working at Guinness Beer. We talk about that because it could be on the test. You never know as I click all my effects buttons. So anyways, we don't want that many degrees of freedom. This is the specific t we are using, 1.9822. We bring that back over here, the t with 1.9822, square root, and then, oh my gosh. If anyone wants to solve this too, go ahead. Oh, those numbers. Gotta square that. Look at all those numbers. Okay. So once again, the major not fun part of this problem for me is all the numbers. Now I always solve the standard error first. So we're going to solve the standard over there on the far right. So that is the standard deviation squared over the sample size for the first group, the standard deviation squared over the sample size for the second group. Make sure to follow your notation. Doesn't matter if you put group 1 or group 2 in whichever order. You're just adding together the two standard errors basically of the means. And let's take 101,953. And the easiest way to miss this problem is to make a math error. Standard error the first, and we copied it. And then we go 165,476.54, square it like we did the other, divide by 72, and add that to the other one, and then square root the quantity. And that is the value of the standard error, 21,914. And we could add the decimals to it. What's the decimals? 82. Hey, Brennan, good to see you here. And then that's the margin of error. Remember, everything after this is the margin of error. We already illustrated that right there. Margin of error is this quantity, and now we've solved out what the margin of error is. The differences between the means are going to be, we're just subtracting those two values up there. 300,744.57 minus 2010 at 260.46. 90, 44, 44, 11, 94, 84, 11, I believe. And so now, yeah, this is the big difference is a lot of people don't use the t, and that's where you create the errors. You have to use the t. The t will give you the exact calculation. Sometimes people miss it by a little bit, and you don't get the points back because you have to use the t. So I've had people email me already saying I was so close. I was off by a few like tens or hundreds or very small amounts. Watch me get it wrong now. We won't. I think we've done everything properly. So there's the estimate. We're gonna go estimate plus 21914.82 and 112. 112,398.93. Now we're going to subtract it twice. If you subtract the value twice, I already copy pasted it. You go back to the center, and then you go down to the lower of the interval. 68569. And the easiest way to make errors on this is to make a math error. This one is a little bit interesting, and it's good practice understanding what you're doing, what the t is, what the notation is, and there's the interval at the end. So let's go right here. Make it so we can see both at the same time. We're going to have to decrease font a good bit. There we go. And a little more. There we go. Good. One more time. One more time. 2 times. There we go. And cross your fingers. That's what you always do. You think I'm lying? Cross your fingers whenever you do a lot of work on my Pearson. Okay. 68569.29. 112,398.93. Oh, really? What did we do? What did we do? What did we do? To the nearest whole. Now, actually, I might give you your points back because it says to the nearest whole number. Round to the nearest whole number. Oh my. Oh my. Uh-oh. Round 95% comfortable. I think it might even change the question if I change it. What wasn't my rounding? Let's check our math again because I don't see any problem. Someone's like, okay, you ready? Let's check my. Did they not carry as many decimals as me on the T? I might actually get very mad at this problem if for some reason, because I don't know the error yet, if we have an error. So let me check the standard errors right here. Did I times the standard error by 1.9822? Did I times it by 1.9822? You know what we can do? Watch this. Here's the best way to do it. Go over R, and I'm going to type everything in real quick. Did you get what I got? Oh, you're getting totally different answers. Okay. So thank you, Jesse, right there. Brian can't math today. Okay, so here's what we're going to do. So we're going to do N1 is 104. N2 is 72. The Y bar 1, it's Y bar technically, but 20.46. There's that. Y bar 2. This is why I love using software. And S1 is equal to 101,953.35. S2 is equal to 165,476.54. And then the T, what's really great, watch this. You can go QT, I think it is. QT, and the percent we want is this, and then 108.08. There's the QT right there. So that's our T stat. There's the T stat. Even more decimals, mirror 1.982. And it'll do plus or minus on this. So we could actually go over to the other side of the distribution and get it, the T stat right here with the 0.975. And that'll be the positive version. That is the 1.9822, but just carried out more decimals. You might be correct, Jesse. So now we just need to write our equation, which is the difference. We can concatenate, yeah. So we're going to go here to the difference. The difference of the two is equal to y bar 2 minus y bar 1 because we want the positive, right? Does that make sense what I'm finding right there? I found the difference. There's the mathematical difference. We could check our work as we look at what we previously did. There's the math difference between those two numbers. Next, we want to do the standard error of difference. The standard error of the difference is the square root of, like do them in parentheses right here. So it's S1 squared over N1 plus S2 squared over N2. There's the standard error of the difference right there. There it is. Now the margin of error is the t-stat times the standard error difference. There's the margin of error right there. And there's the margin of error. Looks like what I was getting, right? And then if we take the difference and we add to it a negative margin of error and a positive margin of error, we should get, oh, diff not found because I used a capital I, didn't mean to. The value's right there. And if we round this right here to 0 decimals, oh, because it's, I should do it. Why is it rounding like that? That's weird. Oh my gosh, what did I do? I'm going to take the whole thing. Brian doesn't know what he's doing today. There we go. Okay. So let's see if this is correct, and then let's find the error. Oh my gosh, Jesse, look at this. I think I didn't times it by 1.96. My gosh, that's what I am pretty certain, Jesse, I didn't times by 1.96. So no, you did it correctly. It looks I bet your answers would have been accepted too. You're welcome, Moira. I am pretty certain when I did this, the error was I didn't times by 1.9822. 1.9822. I really hate that. It's so easy to make a math error. So did I show what this right here, 21914.82. Look at that. That value right there, what is it? For 1,000 points, what is that value? Are you doing the project? Nice. This value, the 43,400, because I times this, the standard error, by the t-statistic. So watch this. Standard error diff. Wait. Oh, there it is, times the t. What am I doing? There it is right there. And it has more decimals carried to it. Does that make sense, Jesse? So I totally forgot the times by the t-stat. That's how it goes. You forget to times by your t-statistic, you get an error. Yeah, so it was math error. There was no theory wrong. The answers you're going to get, this just carried some more decimals. If you look right here, 43,438, 40,439. It's because the t-stat we used, and watch this, if we go here to 1.9822, now we go here to the margin of error, and there it is right there to the decimal. So, and it should take that also. Yeah. But it's just like the more decimals you carry, but it has a plus or minus on it. What is its plus or minus on it? Let me look at the plus. If it has at least a plus or minus of like 5, I hope it has 5. Let me look at the question. So I'm going to have to get it wrong. We are 95% confident that the value is contained within the interval blank to blank. The waterfront is worth more than the non-waterfront. Okay, so it'd be this one. You input your values. Can't copy paste them. I gotta write in the values again. 47,000. Let me see. Would it accept the? I'm gonna enter in 45. I'm entering a little bit off. Yeah, there's a give or take that I think might be a little bit fair on that question. It shows you. I think it shows you too the plus or minus times by your t-stat. Okay. And oh, answer tolerance 194. That is yeah, I'm totally fine with that. That I think you could even use the Z by accident. Maybe that 194. My answer was different on the margin of error by like 2. And then it's got, I think, separate ways it's been calculated here where someone rounded the there's so many theoretical answers. The range for this question is quite forgiving, so I'm cool with it. We'll do the 2 routes here question, but just so you can see the forgivingness nature of this question, just don't forget to times your t by your standard error. There we go right there. Yeah, that is very nice right there. Like if it was less than 5, I'd be like, because I mean, If you carry it to 2 decimals, you're probably fine. Sometimes I do 4 decimals with the T. But here's what's really great, Jesse, is like when I do the T over here, if you look at what I did, it gives me, it just straight finds the T for me. But what if someone said I want even more decimal place accuracy? I could go here and go to options and go to digits and go to 20 digits. And there you go. There's the T to 20 digits. Hey, Harrison, good to see you. When you graduated last year with still, aw. Brendan, we love that right there. And good to see you, Harrison. We're going to do Jesse's question next. So if you really wanted Jesse, you could always carry your T to 20 digits. Yeah, so this is why I love software. It's because it's like, well, how many digits should I carry? And it's like, I don't know, carry as many as you want. But then we should know the concepts that if we give a lot of degrees of freedom, the T, goes towards 1.96 or 1.95996, because that is the, watch here, Q norm. So we go here to Q norm. Norm doesn't have degrees of freedom, though. The T will approach the Z, and the Z is not 1.96, it's 1.95996, but the Z is always lower. We'll usually just say 1.96 because it's basically 1.96. Well, with that, Jesse, it's time for the 2 routes question. Let's right here. The 2 routes question, very similar. So the 2 routes is a notation question. It's going to be very, very similar. But for the 2 routes, you have to look up the T statistic. So the 2 routes question, you have to look up the T. That's the tougher part for a lot of people, is the looking up of the T. 2 routes. We'll find out. Here we go. Man moves to new city. And let me mark this in the video right here. Okay. Okay. So you have to think about what's going on right here. When they move to this new city, basically like that, they have 2 routes they can take to work. So they could take this route here, or they could take this route here. Now, they look similar in nature, but when you take times on these, you would have times from A and times from B. So your times would look like this right here, probably. We could draw the data out. We could look to see if there's what's here. What are we maybe trying to do here with this data? We'd be trying to see what? 'Cause this is the time it takes. So we're trying to see if there's what's between the routes. Hence why it's a 2 sample T. It's B minus A, actually. Kind of, yeah, association. This is a type of association right here. If the time is associated with how long the route takes, you could say if time is independent of route. I mean, sometimes one route might be a little faster, but is there evidence that maybe one route is consistently faster, right? Like maybe on average, B is faster, or maybe on average, A is faster. Maybe we could save up to 5 minutes. Great job, Skylar, there also. Association, dependency, independence, ideas like that. So if, and let's look at the question, when we travel these routes, we're going to go back and grab the question. How long, and you can read through it, how long did it take on average when we traveled route A? Traveling route A took us how long on average? How long did it take us on route A? Route A takes how long? Notation's very important to these problems. How long did it take us on average for route A? A lot of these questions boil down to marking the notation and then solving the problem, and then knowing which equations to use. So route A took, and what is that in notation? If that is the average for route A, what is the notation for the 48 minutes right there? If that is the average for route A, what is that in notation? So that's the average for route A. What is that in notation now? in notation, that would be not mu though, not mu. Good. That's why I asked. Good answer, Jesse. Not mu though. Mu is the truth. So if we say mu, this is the truth, which we really never know. That's the thing in statistics is you really make guesses at mu, and then we don't know the truth for how long route A takes, but we would like to know the difference between route B and route A, the true difference. That's what we'd like to know. It is y bar, and very specifically, it's not just y bar. And great job, Jesse, right there. It is y bar sub A. This is going to be y bar sub B. Y bar 1. And then we can use A and B because when we do the differences down here, we're going to do B minus A. So there's the difference. So what do you notice right away about route B? What would be your guess of the differences? Route B what? We can even plug in the numbers and see what we've already found. We haven't done really any statistics, but plugging in the numbers right here will show us just on average what for route B. Route B is longer by 4 minutes. Yep. So now we don't know exactly how much longer route B is. Like if we were to travel it more times, we need to create a margin of error right here. And the margin of error is going to be the T with the complicated degrees of freedom formula. We're going to do star for the percent confidence we're looking for. We'll find out here in a moment. Then we go square root S sub 1 squared over, we can do the B right there. Since B is first, we could technically do B. Once again,
It doesn't matter!
because you can switch it up right here with B and A. Because it just has to be that the sample size is over the correct standard deviation. You can't do the wrong sample size. You can for this. In this right here, Skylar, B has to go first here, and they specify that in the problem, how they want it calculated, where it says do this right here. This is what we're trying to understand, and this is the sample differences which give us the estimate of the truth. So you do have to calculate it this way, but if you were to reverse the A and the B here, it wouldn't matter because you're just adding things together, and it's the something property of addition that doesn't matter which way you add them. I don't know the names of it, but I do know what it means. Commutative property, something like that. And so with this, yep, it matters which way you do this because then you'll get a negative difference if you do it differently. Now we are going to find the T statistic. Now this is where people usually get stuck because the T statistic has a certain amount of degrees of freedom. We have to go over here to the calculate Welch's T. I've got the link pinned above, and we'll have Mubot drop it in the chat again right here. This is the apps. Thank you to Adam Spanbauer who made this right here, and we need to take our data and let's see what the notation is. We travel each route 15 times, so randomized order, random condition met. And then the first one has a standard deviation of 4. The second one has a standard deviation of 1. So 15, 4, 15, 1. Or 4 for the standard deviation, 15 for the sample, 1 for the standard deviation, 15 for the sample. Degrees of freedom, 15.7432. Now we go back and we calculate the T using a p-value. We enter in the right degrees of freedom. And if we're using 95% confidence, which I think we are, that is our T statistic right there for a 95% confidence interval. 2.1227. And so here we are. 2.1227. And this you definitely don't want to use 2.1227. You don't want to use 1.96. And now we have to go in and plug in the remaining values. And Jesse, as always, if you want to help solve this, you're welcome to, because you know I make errors. Standard deviation 1, 15 squared, 4. What's that? 4? Oh my gosh. Delete that. Okay, and we go here. And we calculate the standard error first. 4 squared, 16, plus 1 squared is 17 divided by 15. There we go. Square root that. That's the standard error, 1.06, times by 2.1227. There's the margin of error of 2.26. So a difference of 4 plus or minus this. And we should be able to do this in our head. This is going to be the lower bound of 1.74 and the upper bound of 6.26. 1.74, 6.26. There we go. I'm doing it in my head, so I'm worried. 1.74. 6.26. That should be right. There's some margin of error. 4 plus. There it is. And 4 minus 1.74. Should the man believe the 5-minute claim that he'll save 5 minutes driving Route A? Yeah, he should. because it's contained in the interval. Yay! We're back on a roll right there. Thank you, Jesse. Also confirming the answer and Scholar confirming it too. Once again, the reason I like using things like jump and R is because if we were to do something like this in jump right there, bunch of King's Quest data right there. If we were to use jump, it really makes our lives easier. And I've got my subset of diamonds over here where I think I made it down to just a certain type of diamonds. Like, let's take a look at it right here. Where did I make the subset? It's really a lot easier in jump to do these things. Like, just life is easy. Analyze, fit Y by X. The cut of a diamond, explaining the price of a diamond right here. There we go. There's the two groups. And now we just go over here to analyze t-test, and there's the difference. What do you notice is contained in the interval for the difference? Chapter 17? Yeah, let's do one next. And Jesse, what do you notice is contained in the interval for the difference? The difference between very good and ideal diamonds. Very good cost on average $623 more. But what do you notice is contained in the interval of the difference? As in, I am 95% confident the true difference between the diamond's price is contained in the interval that ideal might cost $740 more, $745 more, up to very good costing $1,993 more. That's why I'm 95% confident the true difference in mean price of these diamonds is contained in the interval negative 74.90 to 1,993.3. The difference between the cost. So, but what do you, well, the estimate is at the center of the interval, because remember, you have a lower bound and an upper bound, and the estimate will be at the direct center. But what else is contained in this interval that's of interest when comparing two means? A value that is contained within the interval, a plausible difference, is that maybe the difference is 0, and that's the null hypothesis, and the null hypothesis is not rejected. So is it believable that there's no difference between these diamonds? Because 0 is in the interval. And if 0 is in the interval, well, the p-value to test it is also going to be high. So these are the types of things we want to know. So I always like showing the jump output too, so a little bit expanding upon it, because we can run these tests pretty quickly, and it's understanding what the test is doing and why we do it is important. There we go, chapter 17 in the July 2007 issue. Let's go grab that one here. In the July. Go. That's a good one. Good. This is a very big theory question. All right, let's talk first about how to not solve these problems. First thing, I am going to click an answer here. So, would the interval contain 0? No. Oh, love it. Okay, would the 95% conf interval contain 0? Yes, it will. So it will contain 0. Why? Let's have a little fun today. Why will the 95% conf interval contain 0? Well, it goes back to the output we just had. That was mean to me. Let me not be mean, right? You ready? Yes, the high p-value means that we do not have evidence of a difference, so a 0 is a possible value within the conf interval. And I like this a lot because this really goes to the output we just made right here. So when we test two means, what is the null hypothesis? I actually didn't make that error on purpose. I don't know. I misread the no. So the null hypothesis for the two means is that the two means have a what? So the null hypothesis for the two means is we hypothesize that the difference between the two means is what? That the true difference between the two means is what? What would the null hypothesis be? I said I was going to show now how to not do the question. Hey, Kevin, good to see you here. The null hypothesis is that the difference between the two means is what? Is equal to 0, exactly. So if somebody said I ran the test and my p-value came back with this, what are they doing to their null? What are they doing to the null? So your p-value comes back with that right there. And so what are we doing to the null hypothesis? This means we are whatting the null. When the p-value is low, reject the null. When the p-value is high, just let it fly. So what are we doing to the null right here? What does that mean? So they ran their test and they said, okay, that was my null hypothesis of this. But now I came back with this p-value here. So now I'm going to what the null? Reject or not reject. Remember, when the p-value is low, reject the null. When the p-value is high, just let it fly. So they're going to reject the null or not reject the null? Not reject. Exactly. So since they're not rejecting, what does it mean to not reject something? Does that mean we wouldn't believe it or we would believe it? Now, we're not saying it's true. Are we saying what we saw was believable given there's no difference, or what we saw was not believable? Like when I looked at the differences here, I'm saying, yeah, maybe there is no difference, or no, I really think there is a difference. What are we? It's believable. That the difference of 0 is believable. So you're saying what you saw, the p-value is the likelihood of your results or results more extreme given the null is true. So what you saw was plausible given the null is true. So which of these intervals, here we'll do an interval A or B, makes more sense? If I told you the difference in the means is between 80 to 120, or the difference in the means is somewhere between -10 to 30. Which of these is a more plausible interval given a high p-value? So if I tell you the difference of 0 is believable, like seems plausible. The difference of 0 seems like a difference that could be the actual difference. Which of these intervals seems more plausible to you? Interval A or interval B? The interval that B, because it contains 0, because we wouldn't reject 0. So since we don't reject 0, this is what the question is going towards, with not rejecting 0, which is what we hypothesize is the true difference, well, then 0 has to be contained within an interval, and there we go. And so if it had a p-value that came back right here like this, then the answer would be that this is the interval because we have strong evidence at this time that the difference is not 0, that the difference is 0. We have evidence to reject the null because I'm 95% confident the true difference between the means is contained in the interval 80 to 120. That's very strong evidence, i.e. very low p-value, to reject the null hypothesis. Now, this is not how we do the hypothesis test, but the interval will come to the same conclusion. So when you look at this right here, the question again states, we came back with a p-value that was high, i.e. we would not reject that difference is 0. So would the interval contain 0? Yes, the interval will contain 0. This is a high p-value, which means we do not have evidence to reject the null. They say we lack evidence of a difference. So the evidence of a difference is evidence for the alternative, because the alternative is that the difference is not equal to 0. So 0 is a possible value. See, 0 is possible. I should have just looked and saw high p-value and just double-checked myself. 0 is a possible value for the confidence interval. So it has to be contained in because the p-value is high. So yep, be very careful. These are just small questions. But once again, I don't want you to just, I don't want people to just click the answer and then not understand the theory behind it, because it actually relates to this jump output right here. In this jump output, you'll notice that the p-value right here on the two-sided test is high because why? 0's in the interval. So if I were to do something different right here, and I were to go over here to, I think I've got student data set open, and I were to go over here to analyze fit y by x and see if there's a difference between heights of males and females. Well, that's going to be a more obvious one right here when you run it. The difference of 6.48 is 6.84 difference, where males are 6.84 inches taller on average than females. And this difference is ridiculously significant because we estimate that males are somewhere between 5.8 to 7.2 inches taller on average than females. If you notice, 0 is very far from the interval. The difference of 0, which is hypothesized, is nowhere near the observed difference. So we hypothesize 0 is true. That's why it's at the center, because if 0 is true, then the most likely thing to see is no difference. We saw a difference of 6.5 basically, and that difference is very large and not likely by random chance. And when we estimate the true difference, well, 0 is not contained in the interval to estimate the true difference, so we could say there's really good reason to believe that 0 is not the true difference. Lots of really good stuff right here in understanding what you're seeing in the output. And I do want to mention this because we like to talk about what this output means. The T statistic right here for 1,000 points might be one of our last questions of the day. How do we calculate the T statistic with this output run button? How would you calculate this T statistic mathematically given the output on the screen? So remember, our formula is, to get the T for the two sample t-test, is y bar 1 minus y bar 2 over the standard error, which is s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. That is how that's what the T is right there. So how in the world would we calculate this? How would we get that? Does anyone know? How would you calculate that 18.5 if you just had this output? Like if you didn't know this and you had to get that this is equal to right here, 18.51, I think it was. Sloan, great job right there. Let's throw that 1,000 points. Well, we wouldn't use the apps. We'll use what Sloan said right there. And so what is the math for that, Sloan? Because the top part of the equation is the difference, right? Well, not the standard deviation, though. Not over the standard deviation, the standard error. Standard error of the difference, technically. So what is the difference? Isn't the difference right here? That's the difference. Isn't that the difference, right? So the difference is 6.48, right? And then the standard error, it's those values. So we can plug in the values, and that is the difference. So knowing the notation, that's the difference in the sample means. And then the standard error is already calculated for us. There we go. And that's, yeah. Because the difference is literally y bar 1 minus y bar 2. And the standard error is the formula s sub 1 squared over n1 plus s sub 2 squared over n2. Yeah. So knowing these things right here, knowing what the output means is very important. Because a lot of times it can be like, well, what are we trying to find? What does this mean? Why? How could we possibly get the T if we don't have the... Yeah, no worries. Oh, I do stuff like that all the time. Because a lot of times people will be wondering, well, where is... I've had people ask me like, wait, I can't solve the formula because on the formula sheet... Think about this. If the formula sheet says, which it does, y bar 1 minus y bar 2, people will say to me, well, I can't find this because I don't have y bar 1 and I don't have y bar 2. So then I say, well, you do have... I try to like be nice. I'm like, well, you do have everything, but remember what these things mean. What is that telling you? And they're like, sample mean 1 minus sample mean 2. And I'm like, I can't say if you're right or wrong, but if that's what it means, what does sample mean 1 minus sample mean 2 mean? You're finding the difference. So then they say, well, I don't have, like, I can't tell them if they're right or wrong on a test. S1 squared over n sub 1 plus s sub 2, or yeah, there, over n sub 2. And then they say, well, I don't have this. I'm like, well, what does that mean? They say, well, it's the standard error. And I say, okay. And I think sometimes they go, oh, wait, this is the standard error? Standard error of the difference. Yep. I can't say they're right or wrong, but I can be like, well, what does that mean? I'll just usually ask them questions. A really good thing someone told me when you're helping people with a test is you don't want to give anyone new information. You can just ask them questions. So you just say like, well, what do you have? What does that mean? And so if they don't know, they're not going to know. But if they know, they might start thinking like, well, that's the standard error. And I say, okay, do you have the standard error anywhere? Then they look and they're like, oh, wait. So I don't say you have the standard error and use it, but they identify what it is, and I'm like, did we give you the standard error? Hey, Anson, good to see you here. But I like the light bulb moments when I help a student get it by not giving them answers, but by like just talking to them and being like, yeah, because I've had a lot of people get questions like this and be like, how in the world? We do one on the Canvas content like it, so that's good help. And so with that, we will be teaching here in a moment. I have a meeting. Until then, bye for now, everyone. Bye. You're welcome, Jesse. Good work right there. Know your output. Bye. Hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.